So we're going to just kind of jump into the review. Again, whenever we're doing any kind of like practice problems or anything, if you don't even have to ask to get one. If you want to grab a whiteboard marker to use it, whenever, that's fine. You can always just grab one and then, just put it into the other like basket after. So what I did is I started actually doing in-class review a couple years ago when a lot of people just had general questions about stoic and solutions and ionic equations, things like that. So I figured our time would be better used to actually just go through some practice problems, and I'll try to answer questions in any way that I can. So if you are confused on something, you're not sure where I got a number, just ask. Sometimes I just start going through problems and not realizing that I'm just working through a problem and pulling numbers like off the periodic table or something else. So these slides are on the lesson plans, Google Classroom, and on the class website. So we probably will not get through every practice problem in class. That's fine. But any additional problems are there, and I actually always put my work up as well. So on the website and on my lesson plans, you'll see the answer key. It just says like work or answer key, but I take my notes, everything worked out, and I put it on there as well. So some things that aren't covered in this that you still need to know. So besides chapters 1 and 2, things like knowing reactants versus products, particle diagrams is going to be really important. So there were some mastering questions that looked at particle diagrams. Can you take your reactants in a balanced equation and figure out products? Things like that. I do have a particle diagram question that we will look at in the Do Now tomorrow. So even though you guys will be online, I still have the Do Now slide up for those that were online today. Balancing equations, so just balance, put your coefficients, types of reactions, and then figuring out molar mass and using Avogadro's number like we did in the post lab. So most of this is sections 3.1 to 3.4. If you did not get a textbook and you want one, even just to review for this test, I have lots of extra textbooks because the now seniors finally brought their books back in at the end of the summer. So if you do want a textbook, I can give you one at the end of class. But this all is covered in 3.1 to 3.4. There is all of my Chapter 3 videos as well and examples. Those are all posted on the website. So under summer work, you'll see Chapter 3 as well. So some of the questions we look at will be multiple choice. Some will be short answer. This is an example of a multiple choice question. And this is going to have us practice actually balancing specifically combustion reactions because those are usually the most difficult to balance. And so this says complete combustion of a sample of a hydrocarbon in excess oxygen produces equimolar amounts of carbon dioxide and water. Which of the following could be the molecular formula for the hydrocarbon? And so what I want to do is look at some different terms in here. So it tells us that we have combustion, and then it says that it produces equimolar amounts. You'll start to see this word very often. So equimolar just means equal moles. So it means that it produces equal moles of carbon dioxide and water. Which of the following could be the molecular formula for the hydrocarbon? Now sometimes there's nothing else that we can do besides try each one of the options. Now this says complete combustion in excess oxygen. So that means, if you remember, for a combustion reaction to occur, it's a hydrocarbon plus oxygen. Oxygen is diatomic, so it's O2. So each one of these will be plus O2. And it even tells us the products in this. It says carbon dioxide and water. Carbon dioxide, water. So now it's just a matter of balancing. Now I'm going to show you a trick for balancing combustion. Trick for balancing combustion reactions is to put a 2 in front of the hydrocarbon. So put a 2, before you start anything else, put a 2 in front of this. 2, 2, and 2. Usually that will help prevent any odd numbers from occurring. Right? Odd numbers of like oxygens is usually what we see in combustion reactions. The order that you want to balance is C, then H, then O. Always save O for the end. So if I use this 2 to start, right now how many carbons do I have here? 4. I only have 1 over here, so I'm going to put a 4. Same thing, I have 2 times 2, so I have 4 hydrogens. I have 2 here. So that gives me, here's where you want to be careful with combustion. I have oxygen in 2 places. So I have 8, 9, 10 on the right. I have 2 here. So what can I put in front of the O2? 5. So by putting this 2 in front, it helped us from having to double things. It's just a little trick. So same thing, if I balance this one, that's what, 4, 4, 12, 6. So there's 8 and 6, 15, 7. Yeah. And then, let's see, there's 8 and 8, 16, 16 and 8, 24. Now, what do you notice about all of these coefficients? 2, 12, 8, and 8. So I have 2, 12, 8, and 8. And so they're all even numbers. So I'm going to divide them all by 2. If you can divide by 2, or you can divide by 3 or 5, right? You always want to make sure they're the lowest whole number possible. So this would be a 1, 6, 4, 4. And then 12, 12. And then there's 24 and 6, 30. So here's the important thing now, is that it says it produces equimolar amounts of carbon dioxide and water. That means that when we burn, when we combust, we should have equal numbers, equal moles of CO2 and H2O. Which one of these answer choices produce the same coefficient for CO2 and H2O? C. Right, that's our answer. So sometimes that's all, like we have to actually go through and figure it out. But the important thing here is that it said it produced equimolar amounts of CO2 and H2O. Let me answer. Yep, okay. So that's looking, I guess we did review balancing, but more specifically, this was reviewing combustion. Usually the most difficult ones to balance. But if you remember that 2, it should work out. And if you can divide by 2, right, if they're all even, then you can reduce. So now looking at stoic, so what is the mass of oxygen in 148 grams of calcium hydroxide, CaOH2? So when it comes to anything with stoic, always start with your given piece of information. Right? Even if you're like, I have no idea what to do, where to go with this, start with your given piece of information. So my given was 148 grams CaOH2. So when you have a given piece of information, even if you're like, I have no idea what to do, The first thing you can always do is convert your given to moles. So the first thing I'm going to do here is I'm going to take my grams and I'm going to go to moles. So just like we looked at in the post lab, 1 mole of calcium hydroxide. So we look at our periodic table and we have 40.08 plus 2 oxygens, 2 plus 2 hydrogens. We always use 1.008 for hydrogen's molar mass. Essentially just use what's on that periodic table. That yellow periodic table is the exact periodic table you're going to get on every quiz and every test. So on Wednesday's test, you're going to actually have a laminated version of that periodic table. And so when you add everything up, I got 74.096 grams. That's the molar mass. All right, this is the molar mass of calcium hydroxide. So the first thing that I did, I'm going to cross this out so I can see that my unit's canceled. The first thing I did was I took my given information and I went to moles. Now the problem doesn't want moles of calcium hydroxide. It wants me to eventually get to oxygen, more specifically grams of oxygen. And so what I have to do, even though I don't have a balanced equation, if I want to go to something new, I need to use a mole ratio. And I want just O. It doesn't say oxygen gas. It's not O2. It just wants the element, right? The single atom. So for one calcium hydroxide, how many oxygens are in this formula? 2. All right, so for every 1 calcium hydroxide, there are 2 oxygens. Now the problem doesn't want moles of oxygen, it wants mass. So it wants grams. So for every 1 mole of oxygen, you have 16 grams. This is just oxygen, not oxygen gas. Oxygen gas would be O2. Just oxygen is just the element. So notice I've been crossing my units out as they cancel. So to calculate, you'll do 148 times 2 times 16, divide by 74.096. And I got, to 3 sig figs, 63.9 grams of O. Now something to keep in mind is when you're looking back at your answer, look at what you're given. So I started with 148 grams of my entire substance. It should make sense that I have less than that for just a single element. So within this, we have 63.9 grams of oxygen. So that's just using stoic. We also could look at mass percent, right? Part over whole. So if they said we have 63.9 grams of oxygen and 148 grams of calcium hydroxide, what's the mass percent? It's just part over whole. So we would take 63.9 divided by 148. So again, that's just looking at stoic, taking it a little bit different with single elements. Questions on this? Okay, we're going to jump into empirical formulas next. Empirical formulas are questions that can be in either multiple choice or free response. So with AP, we have 2 sections of all of our tests because it's just like an AP test. We have multiple choice, we have free response. There are always empirical formula multiple choice questions. Why? They decide that those are good multiple choice questions to ask. So empirical formulas, just a quick overview. They are the lowest whole number ratio of atoms. So your subscripts are as reduced as possible, but they're still whole numbers. Now, how to find it? So how to find an empirical formula. And I say this over and over in my head, just like with the solubility rules, and it kind of sticks. So how to find empirical formulas. You take percent to grams, grams to moles, divide by the smallest, multiply till whole. So percent to grams, grams to moles, divide by the smallest, multiply till whole. Now this multiplying, we don't usually have to do. This is if you end up getting numbers like 1.5, 2.5, 2.25, and you can't have those as subscripts. So usually we do this up here. Percent to grams, grams to moles, divide by the smallest. The whole point is to find the ratios of every atom to each other. And so if you're given percent to start, this is where you start. If you're given grams, we can just start with grams to moles. So here's an example. This was a multiple choice question. So a lot of times if you see multiple choice questions that I'm asking, they were at one point on some sort of AP test. So an ion containing only oxygen and chlorine. Okay, so we know that the only thing present is oxygen and chlorine. Is 31% oxygen by mass. Right, so that means that I have oxygen and I have chlorine. So it's 31% oxygen by mass. So remember the first thing is percent to grams. So 31 grams. If it's 31% oxygen by mass, that means the rest of it's chlorine. So what's the percent by mass of chlorine? 69%, so 69 grams. If it's 31% oxygen by mass, that means that it's 69% chlorine by mass. So, steps for an empirical formula. Percent to grams. That just means you drop the percent sign and change it to grams. That means we can assume it's a 100-gram sample. So, percent to grams. And the next thing is grams to moles. So this is oxygen, so grams of oxygen, moles of oxygen. How do I go from grams to moles? What do I have to use? Yeah, the molar mass. This is just elemental oxygen. There's one oxygen there. So it's 16. And then chlorine, 35.45. Again, it's just elemental, not diatomic. So percent to grams, grams to moles. Now, here's a thing that I want to make clear with doing empirical formula problems. Be careful to not round your answers too soon. So when I do 31 divided by 16, I'm going to actually write out this entire number, 1.9375. If you round too soon, so if you were to just put 1.9 here, you could actually get a lot different numbers. So 69 divided by 35.45 is 1.946. All right, I'm going to go out to the same number of significant figures. So we went percent to grams. We went grams to moles. The next thing is to divide by the smallest. So which of these numbers is smaller? The top one, right? So I'm going to divide by 1.9375. Because the point is, once you've gone to moles, the point is to find the lowest whole number ratio. So we're looking for ratios. This is 1. You should always have one of them that equals 1. And then 1.9375, we get 1.00. Here's our ratio. There's no need to multiply to make whole because our numbers are already whole numbers. That means I have one oxygen and 1 chlorine. So when I look at my choices over here, which one matches 1 oxygen and 1 chlorine? A. So this is an empirical formula question. Percent to grams, grams to moles, divide by the smallest, and we got our answer. The only time you have to multiply till whole is if one of these, let's say this was 1.5 instead. You can't have a ratio that's 1 to 1.5. You can't have a subscript that's 1.5. So you have to multiply to make it 3. If you multiply one of them, you have to multiply the other one as well. Okay, so let's look. I'm going to kind of skip through some of these because I want to make sure that we get to, so you can do hydrates the same way. I'm going to just set this up. We won't necessarily finish the calculation because I do want to get to a special type of empirical formula and I want to give us time to go through that problem. So a sample of a hydrate of copper 2 sulfate with a mass of 250 grams. So hydrate means that you have a substance with water. So this 250 grams is CuSO4, and hydrates look like this. And there's some number here. That's a hydrate. A hydrated compound has water attached to the crystal structure. So the sample of the hydrate was heated until all of the water was removed. The sample was then weighed and found to have a mass of 160 grams. So that means once we've removed all of the water, this is just CuSO4. What is the formula for the hydrate? So we can treat this hydrate problem just like an empirical formula problem. Except now I'm going to, instead of having individual elements, I'm going to have CuSO4 and H2O. So it tells us that when all of the water was removed, there was 160 grams of copper 2 sulfate. The law of conservation of mass says that mass can neither be created nor destroyed, which means if we had 250 grams to start with, that was the copper 2 sulfate and the water, how do I figure out how much water was lost? Subtract them, because 250 minus 160 gives us the amount of water that was removed through the heating process. And now you would go through this empirical formula problem the exact same way. So we already have grams, right, which means we don't worry about percent to grams. So then we go grams to moles. Instead of individual elements now, we find the molar mass of CuSO4. Same thing for water. All right, we find the molar mass of water. So we did grams to moles, and then we would just divide by the smallest, and that would actually give us our formula. Now when you divide by the smallest, this is a 1. I think this is a 5. Let's see. Yes. All right, so once you, I'm going to do this because I'm going to put another equal sign just so you remember. When you divide by the smallest number, this turns into a 1. This turns into 5.00. This is the ratio of copper 2 sulfate to water. So that means you have 1 CuSO4. And hydrates are always represented by dot, certain number of H2Os. So when it says what's the formula for the hydrate, it'd be CuSO4.5H2O. So hydrates can be used in the same manner when you're looking at these empirical formulas. All right, so next I want to talk about a special type of empirical formula question. This is new for AP Chem. So This was not covered in honors. There was some stuff on the summer work about it, but I still like going through it because it's essentially an applied empirical formula type of problem. And it's called combustion analysis. So combustion analysis is a real-world example of determining an empirical formula from lab data. In a combustion analysis problem, it's only done so since it's combustion, it has to be a hydrocarbon, which means CH and sometimes O. Sometimes instead of O, it could be replaced with N, but it still has CH and then another nonmetal. So when it goes through combustion analysis, all of the carbon that is in this unknown hydrocarbon is converted to carbon dioxide. All of the hydrogen in the hydrocarbon is converted to water. And then if a third element is present, like O or N, then its mass has to be determined using the law of conservation of mass. So you have to subtract C and H from the original sample to figure out what mass of unknown you have left. Now there is an example in the textbook. It's 3.15 on page 101. So again, if you want a textbook, I can give you one. And this example walks you through step by step on a combustion analysis problem. I also have a combustion analysis example within chapter 3. So if you want to watch another example, there is one in the YouTube playlist for going through combustion analysis as well. So this is just what it is, how it's determined. But we're going to actually look at an example. So this says quinone, which is an oxygenated hydrocarbon. So oxygenated hydrocarbon means oxygen, hydrogen, and carbon. So we're going to have C with some subscript, H with some subscript, and O with some subscript. So I'm using X, Y, and Z as our subscripts. So it's used in photography. When a 0.144 gram sample is analyzed by combustion analysis, so this is the sample mass. So that is C and H and O. 0.352 grams of carbon dioxide and 0.0480 grams of water is produced. Find the empirical formula. Okay, so we're going to go through this step by step. So the first thing that we're going to do is we're going to determine carbon in the sample. So we're going to determine the mass of carbon in the sample. Now essentially what this is just using stoic and empirical formulas combined. So the first thing we have to do is we have to go through and we have to look at stoic. So I have 0.352 grams of CO2. When this hydrocarbon is combusted, 0.352 grams of carbon dioxide is produced. Now I want just the mass of carbon, not all of the carbon dioxide, just the mass of carbon. Which means I have to now stoic from grams of CO2 to grams of just C. Now unfortunately I can't just say grams of CO2 to grams of C, I have to go through the whole process. So I'm going to go grams of CO2, if in doubt, go to moles. So I'm going to go from grams of CO2 to moles of CO2. I'll fill my numbers in a second. I'm just going to get the outline first. So I'm going to go grams of CO2 to moles of CO2, then moles of CO2 to moles of just C. So essentially what I'm doing is I'm taking my mass of carbon dioxide and I have to go back out to grams of just carbon. So I need to take my given and go to moles, use the mole ratio to go to a new substance, and then go back out to grams. So now I'm going to fill these numbers in. So to go between grams and moles, that's the molar mass. 44.01 grams of CO2 is 1 mole. Now if I look at this, for every 1 CO2, if I look at the formula, for every 1 carbon dioxide, how many carbons are there? Just 1. So it's a 1-to-1 ratio. And then for every 1 mole of carbon, right, molar mass is 12.01. Now this works that like this is a 1-to-1, so if you forgot this, it wouldn't actually hurt you. But that's only for CO2, because for H2O it's not going to be the same. So I can take 0.352, multiply by 12.01, divide by 44.01, and I got 0.09606 grams of carbon. So there is my grams of carbon that came from this sample. Now I'm going to do the same thing for hydrogen. And the reason that I'm going through and I'm doing this is not because I like doing stoic, but it's because in order to determine an empirical formula, remember it's percent to grams, but we don't have percent here. But then we have to be able to go grams to moles of each individual element. And so what I'm doing right now is I'm taking all the information and going to grams so I can actually start the empirical formula. So the second thing that we're going to do is determine grams of hydrogen in the sample. Now remember that all of the hydrogen from this hydrocarbon goes into water. There's only one place for carbon to go, CO2. There's only one place for hydrogen to go, H2O. So I'm going to start with 0.0480 grams of H2O. Now I have to stoic from grams of H2O all the way to grams of just hydrogen. So I'm going to take my given information and go to moles of H2O. So the molar mass of water is 18.016. So I took my given information and I went to moles. Because I don't want grams of water, I don't even want water. I need to go to just hydrogen. So for every 1 mole of H2O, because I need to go to a new substance, I have to use a mole ratio. To go from H2O to just H, remember we just want elements. In 1 H2O, how many H's are there? 2. So this is not just a 1-to-1 ratio. There are 2 moles of H for every 1 mole of H2O. And then hydrogen has a molar mass of 1.008 grams. So we'll go through 0.048 times 2 times 1.008 divided by 18.016 gives me, no, I 3-hole punched my answer. Right, so 0.048 times 2 times 1.008 divided by 18.016. 0.05371 grams of hydrogen. So now we know in this sample that contains C, H, and O, we know how much carbon we have, we know how much hydrogen we have. Now in order to figure out the empirical formula, I need each individual atom. So I need oxygen. So the next thing that we need to do is we need to determine the mass of O. Now please, 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 please do not try to stoich from CO2 and H2O to figure out oxygen. That's going to be way too much. Here's what you can do. Here's the total sample. 0.144 grams is the total sample. Well, total sample consists of C and H and O. So C, 0.09606, plus H, plus, I'm just going to do X grams of O. It's a lot more simple than trying to stoich everything. So 0.144, I'm just going to subtract both of them, minus 0.09606 minus 0.005371. .04257. I'll just keep them all out to 4 sig figs. There's my oxygen. So now we have all of our grams of our elements. So now we can go grams to moles divided by the smallest. All right, so I could take this 12.01, 1.008, and 16 in 1 mole. And then you can find the moles, divide by the smallest one. So if I do 0.09606 divided by 12.01, 7998 moles of C, 0.05371 divided by 1.008, 5328 moles of H. And then if I do 0.04257 divided by 16, 0.02661 moles of O. So empirical formulas, percent to grams. We don't have to worry about that. Grams to moles, divide by the smallest. So this is the smallest number. So divide each one of these numbers by this 0.002661. Right, so if I divide divided by, this is 3. This is 2, and then this is 1. This is my ratio. These are not my subscripts. So we have C3H2O. There's our empirical formula. So that's like an applied empirical formula type question. Now again, there are more problems in this slide, like in this slide deck. They are posted on the website, lesson plans, and on Google Classroom. If you want the answers, pull them off of either the lesson plans or the class website. The class website has lots and lots of resources. Tomorrow we'll focus on Chapter 4, but as you work through, if you have questions, please just send me questions via email or remind, and I think that's it. There is like a review. There's review questions. Yeah. So on the website, if you go to summer work, and then there's a tab that says test reviews, there are practice questions for 1 and 2. Yep. Yep.